Okay, so we are really great in time, and yeah. So I have the honor to announce the next speaker. So this is Luca Verre from Prophesee, and he will talk about revealing the invisible to machines with neuromorphic vision systems. So I'm really excited about your talk, and the stage is yours.
Thank you. Thank you very much. Thank you, everyone. I'm Luca Verre. I'm the CEO, co-founder of Prophesee. It's actually exciting to be here for two reasons. The first one is that this is our first event after pandemic started, and second is because it's a great show. So I'm also excited to share with you some insight about neuromorphic vision technologies and how this technology is now creating a new paradigm shift in machine vision and AI, and the way actually at Prophesee we are leading this paradigm shift. I will explain a little bit about the technology, about the foundations of the technology, and then walk you through a few applications in the field of machine vision. I co-founded Prophesee 7 years ago with actually first application in the medical field. So we are actually the pioneers in this field of silicon retina. The first chip was actually used for vision restoration of blind people, is what you see on the top left of the slide. The first silicon retina we implemented was actually to restore sight of people who have a certain degeneration of the retina. Because in fact, the human eye is not producing an image. The human eye is actually generating event to changes that are happening in the scene. And this is actually what we do at Prophesee. Prophesee is developing artificial model of the human eye. So we develop a vision sensor that mimics the eye, and we develop computer vision and the AI algorithm which mimic the brain. By now, the company is about 100 engineers. We have location in Europe, in the US, in China, and Japan. We are the pioneers in this field, so with more than 50 patents, with more than $80 million invested, with investors such as Intel, Bosch, Renault, Nissan, and some other investors that are supporting us in this mission to actually lead this paradigm shift. Our business model is very simple. We develop the silicon retina, the sensor, and we develop also the software stack to process the event for both actually computer vision and AI. And on the right side, actually, you see some of the partners and customers that are working with us, that together with Prophesee are embracing this vision that the human eye is actually a great model for machine vision and artificial intelligence. The way we actually emulate biology at Prophesee is by actually implementing a sensor where each single pixel is independent and asynchronous. So we embed some sort of intelligence inside each single pixel. So in fact, the sensor doesn't work in the way like many other sensors work in the industry by generating a sequence of images at a fixed point in time. Our sensor, like the human eye, is reacting to changes. And the way we do it is by making pixels that are smart, embedding some level crossing sampling circuit that basically make the pixel capable to detect when there is a change in the scene. Like you see in the video, when I start moving, I will produce events, which are typically related to some edges, to some contours of the object. If I stop moving, then there are no any more data being produced. This has three major benefits. The first one is straightforward, is that because I'm only reacting to the changes, as long as there are no changes, there are no data, so the acquisition becomes extremely efficient. The second benefit is the fact that the acquisition can be actually very fast, with time precision of microseconds, so the equivalent of tens of thousands frames per second, but only for what is changing, because effectively there is no an image. In fact, as you can see, there is no image. And the third benefit is that we have an asynchronous per pixel exposure, which make actually the dynamic range of the sensor very wide. So therefore, the sensor is very robust to changing lighting conditions. So three benefits which are key, especially in the application of machine vision, not necessarily in the application of imaging. So this technology, inspired by biology, has some sort of fundamental root in actually being suited for processing rather than pure imaging. And how we compare with a conventional imaging approach is very easy. So on the left side, you have a video that everyone is familiar with. It's a sequence of static picture, of static representation of the scene, and actually understanding. So the first drawback of this approach is that we produce a lot of data which are useless, like, for example, the background doesn't change, and actually the fact that we are acquiring a fixed point in time, so between images we lose information. On the right side, you have the equivalent scene recorded by a Prophesee event-based sensor, and as you can see, we only focus on the changes in the scene. So, for example, my eyes that are blinking, my hand that is moving, etc., etc. So the background, for example, which is static, is not being acquired over and over. So as you can see, you can visually appreciate the fact that the amount of data is drastically reduced. So not only about efficiency, it's also about speed, as we said. And the way we like to show the speed of the sensor is by, for example, recording a scene where we have a white disk with a black dot that is rotating. And what we do is that we actually display this event in 1 second time window, where actually on the left side we display what you would get with a conventional frame-based sensor, so sequence of images, a fixed point in time, where actually sometimes it would be extremely difficult to understand motion. Think for a second if you had a camera running at 10 frames per second with actually this disk rotating at 10 rounds per second, essentially you could potentially argue that the disk is actually static, while actually is not static but is moving, right? On the right side, actually, you have the event-based sensor that is reacting as soon as the pixel translated from one to the other, generating this time-continuous spiral of event with time precision of microsecond, so which give you this information that revealed invisible between frames. So this is our fundamental claim. So bottom line of this long story is the fact that understanding motion is much easier with this approach. So in the summary, key benefits are in terms of speed, in terms of efficiency, in terms of wide dynamic range, so more than 120 dB, and overall with the fact that at the system level you benefit from this acquisition that is power efficient and in terms of processing also efficient as well. So at Prophesee, as I said, we develop both the sensor and the software. So we are a fabless company. We have been implementing so far 4 generations of the sensor. We also provide to our partners, to our customer, the entire software stack to build application for both machine vision and AI. Actually, Sony Semiconductor Solution released a few weeks ago the announcement about our 4th generation of the sensor, which has been co-developed together with them. So Sony has announced 2 references, a VGA and HD sensor, which is using a very advanced technology process in manufacturing. It's a BSI 3D stack process, which led us actually to reduce the pixel pitch to 4.86, which is actually the smallest pixel pitch for an event-based sensor. It's actually the first event-based sensor with such a resolution that is today commercially available in the marketplace. So for us, it has been a great experience, and of course, working with the market leader, Sony, is of course a great boost of confidence and commercial success. So together with the sensor, as I said, we also provide the software tools to enable our ecosystem to build the full application. So we have implemented more than almost 100 algorithms, code samples, ready-to-use application, which are grouped in category related to machine learning, computer vision, 3D, et cetera, et cetera. We spend also a lot of our resources to implement machine learning tools for inference, for simulation, for training. We also provide actually very large event data set, which is labeled, so that everyone can actually take over the technology and start some easy experimentation with it. And 6 months ago, we also decided to release an open source architecture for the software, because we wanted really to enable a community as wide as possible to start actually work with the technology and embrace together with us this journey. So, and by now we have more than 500, 600 clones already actively working on our OpenEB. Now, talking a little bit about application, where we use this technology for what. So let me walk you through a few examples of implementation. So one example is particle size so particle counting and particle size monitoring. In this is quite a straightforward application in the sense that because our sensor is only reacting to what is changing in the scene, basically doing the scene segmentation is actually pretty straightforward. And we can use actually this information to count and measure the size of the object with extremely high precision. In fact, as soon as the object is translating from one pixel to the adjacent pixel, this give us a new event that we use to update the tracking model, making the tracking actually extremely robust and precise against, for example, occlusion. So we can reach KPI up to 500,000 pixels per second in terms of speed with precision that are close to 99%. So this is a quite unique implementation, and I would say even straightforward implementation of the technology. Second is vibration monitoring. Any machine is vibrating because there is some sort of motion related, and actually it's very interesting to measure the speed, the amplitude, and the frequency of vibration. Why? Because typically drift in amplitude or frequency of vibration give you a first indication of a possible failure mode of a machine. So we do that because based on this information, you can start running some predictive maintenance routine and therefore reduce the downtime of the machine. We can measure frequency which go from the range of few hertz to kilohertz with accuracy again of the pixel level, right? You need to actually rethink a little bit the way you do computer vision and AI, because it's not the same approach. It's not anymore related to a static understanding of the scene, but you try really to extrapolate information from where the information comes from, which is typically some motion. And last example I wanted to show to you is pattern monitoring, because this plays actually with two key benefits of the technology. One is speed, one is dynamic range. It's a situation that happens in laser welding, in machine tools, for example, metalworking, etc. This video is actually slowed down many times to actually show you the way we detect and track spatters that are generated by the laser welding process during the welding of the metal part. Why this is relevant? Because typically you want to detect and size these spatters, because from this information you can infer about the quality of the welding, and then you can apply some closed feedback loop to control, for example, the speed and intensity of the laser to do this quality management in real time. So this is not only is quite unique in the sense that we go very fast, but also given also the bright conditions of the scene, you would need also a very wide dynamic range sensor to monitor this application. So in this case, we have up to 200,000 frames per second equivalent rendering and simultaneous XYT tracking of the particles. So all these applications now are, we make this application live thanks to partners. I'm glad to see actually in this show many partners that are today working with us. For example, CenturyArcs or Imago that have decided to adopt our technology and build industrial camera. So on the left side, Imago is building a USB camera that is connected to a box PC for some software implementation, and Imago that is building a smart camera with an embedded SoC for local actually processing, also for industrial application. So both actually are running on our generation 3, which is the VGA version, which we have been actively promoting until recently. And then, as I mentioned, our latest generation, generation 4, which we co-developed with Sony Semiconductor Solutions, is now available. Sony made the announcement 3 weeks ago, and we are very glad now to be able to provide development kit and evaluation kit running on this Sony co-developed sensor on the platform you see actually in the slide, which come with different features that I would be glad to give you more details if you come to visit to our booth later on. So thank you for your attention. I hope you enjoyed. If you have any question, happy to answer to you. Thank you.
Yeah, thank you very much, Luca, for your exciting presentation.
Thank you.
Unfortunately, I don't see questions here on my desk. Yeah. For me, maybe this is a...
I don't want to put you on the spot.
Yeah, no, but maybe it's a silly question. Your business model is a license of your technology, or you're not a hardware vendor, you're a software and company with the expertise in sensors.
Yeah, we are first of all a sensor company. We are fabless. We actually design the sensor ourselves, but we don't manufacture it. That's the reason why, for example, we work with Sony in this partnership where they actually gave us access to their very advanced technology process.
Yeah.
And together with the sensor, we also provide a software stack because we know that we come with a technology paradigm which is very different from the way the industry is currently working on, and they have been working on for many, many years. So the reason for us is to also enable the partner to actually get familiar with the technology and be able to, in a very easy way, to use it. So we are a technology provider in the end, so we work with some of the partners here because we need to enable them to build cameras, to build camera system, camera modules, etc. But yeah, so.
Yeah, okay, thank you. Maybe a second thing is the application you introduced, were, let's say, very interesting and exciting, and probably something that is difficult to cover with the traditional technologies, but it was, let's say, more not really classical machine vision applications. Yeah. So I think that's, for me, it was very interesting. Do you want to comment?
Yeah, I mean, when you come with a new technology in the market, you try always to enter from the problem that the customer are not able to solve, because if you show something which is marginally improving what the customer is looking for, it's difficult. The switching costs are too high to actually justify the fact that, okay, yes, I get a marginal improvement, but I need to invest in a new technology, I need to invest internally to train my people to adopt this technology, etc. So that's why we started looking for application where there is a clear need, and unmet answer from the incumbent technologies, and then our objective is to progressively, of course, grow up in the market and cover also application where maybe today we are nice to have.
Okay, so again, thank you very much.
Thank you.